Okay, so without further ado, today I will talk about the results we have been, so far obtained based on this approach we call data assimilation. Right? That's the main theme of this talk. Let me move forward. Brief outline. I will start with a brief introduction about data assimilation modeling in general. And I will spend actually most of the time talking about the work we done for Western US Mantle Dynamics and how that affect the surface responses in various ways. Then we will move on to a general discussion about subduction dynamics, especially on a global scale, below other continents, for example. Eventually, I will say something about this line of research. Eventually will shed some new light on the understanding of Craton evolution, which is a relatively new topic. Of course, in the end, I will provide a brief summary. So to get started, geodynamics, as you can imagine, is basically a discipline that studies the Earth system behavior, right? As this cartoon shows, Earth system, most of them are, open systems, right? We usually have the definition of the system that you have a kind of like a body, right? And or an organization, whatever you call it, and then you have input, and that organization can give you output, right? And this body itself also has like surrounding, basically outside or exterior and interior by definition, and then there will be a boundary, right? So this is a sketchy way of talking about a system. So to put it into more terms, and the inputs could include like a boundary condition, initial condition, like for Earth's problem, like the system properties, in this case, Earth's property or rock property, right? And the output here may include the deeper interior, like from the surface, of course, all kinds of dynamic processes, and also at the surface, we can have all kinds of responses. So this is especially what we concern about, because this is where we make observations, right? And for Earth dynamics, of course, the 4D evolution is the main theme always. So then what is an Earth system? And this is a general way of describing a system. For Earth system, we know that, well, actually, there's still some more terms. I mean, for Earth system especially, right, the problem is that the inputs usually would have uncertainties, and correspondingly, the output may have non-uniqueness, right? This is actually a very common problem for Earth problems. So the Earth system, if we look at the spatial distribution, it can include like the exterior here we defined at the outer space, and the interior, of course, is the mass, right, of this planet. And talking about the interior itself, we can still divide this into many different layers. For example, the surface, the water layer, right, the Craton sphere or the hydrosphere, whatever you call it, and the rocky interior, or the high density interior, the cross mantle and the core. And among these layers, of course, there are always boundaries, right? Across these boundaries, you have mass and energy exchange, and that's how this dynamic system works in general. And this is like a static view of the current configuration. But if you look at the temporal evolution, that's another dimension, right? The Earth system, by definition, is a 4D system. Looking at the time, we know Earth's history has at least 4.5 billion, right, of history. So the very beginning, of course, is the lump sum formation of the planet Earth, where we put all the mass together, and very quickly in the interior, it's basically settled down into layers, like an onion, right? Like, for example, the innermost part is the core. But of course, the internal layers, actually, most of the layers will stay like that, but except the core, because the inner core actually formed quite late, in this case, about like 1 billion years ago, right? And that's a fairly new discovery, of course. Then at the surface, with time, we have all kinds of evolution as well. For example, the continental crust will form very early on in the Earth's history, and then you form the lithosphere and form the Craton, and afterward, you have the supercontinent cycles that's shown here, right? And during this course, you also have a relatively uncertain or still being debated, like the timing of the global scale subduction initiation, right? This is actually a hot topic right now. So this is the bulk part of the Earth. So at the surface where we live, we care a lot about the environmental change, like climate change. For example, this is the climate states where I'm only showing the the cold seasons, right? The snowborn ice ages. And you can see that they are kind of scattered around, and people are still wondering what caused them and what are the implications. Again, we have this other interesting phenomenon, including ourselves, that's life, right? Life started on Earth really early on, but it really only started to explode crazy around the time of Neoproterozoic or Cambrian, actually. So related to that, we care about the oxygen content in the atmosphere, right? You can see that the oxygenation events, there are actually at least 2 of them. They are quite dramatic and very puzzling. Then talking about temperature, we have this relatively coarse record throughout almost the Earth's history. And very often people talk about the CO2 fluctuation that is usually going along with the temperature. So far, the whole point here is showing that the Earth system is a highly multi-dimensional, multi-variable, very complicated system, right? So to understand this system apparently is not an easy job. So to some extent, you can see that understanding the Earth system may look like a blind man touching an elephant. And many people use this example. And also many people use this famous quote, our models are wrong, some are useful, right? And this is understandable. And we know that because, as I said in the very beginning, the system of the Earth is so complex that many input parameters to a so-called model are uncertain, right? And therefore, that's why different observers will get different results, and because the sampling bias of each person. So the question now is how to reduce this model non-uniqueness, right? How could we improve our prediction power, right? How can we more uniquely understand something on Earth and make a prediction event, right? So let's start from math, right? Mathematics. When we talk about Earth system, you can think about this in a mathematical way. This is actually a common language everyone can speak. And for example, Earth system is very often like a partial differential equation, right? AS equals B. Like the big matrix A here, according to Earth problems, it can be basically determined or described by like a governing equations of the mantle of the Earth and the rheological laws of the rock and the temporal evolution of the system, right? They all formulate this big matrix, right? There's a lot of these like behavior properties. And in terms of the unknowns of the system, you can imagine this can include like the boundary condition, the initial condition, the rock or the material property of the system, etc. And then talking about the constraint or the knowns of this mathematical equation, we can have the present-day Earth structure from seismology, right? The 3D structure, very well imaged now, and of course it's still getting better. And the surface, we have the tectonic records that pretty much cover the geological realm of things. And usually we believe that is a reflection or a manifestation of the internal dynamics. And of course, on the surface, we have the climate, the environmental, ecosystem, whatever behavior. That is a kind of a relatively unique line of record because that's what we care a lot about right now. So now the question is, how could we get a unique solution from this very complex equation, right? And we know that a unique solution from a mathematical point of view is that you need to have a well-determined problem, right? In other words, the number of knowns or observational constraint should be no less than the number of unknowns, or in this case, the system variables. Then for an Earth question, right? For an Earth problem, which is naturally complex and multivariable, so how do we construct such an equation such that we can eventually get a unique solution? So I will not say this is the only solution, but data simulation is definitely a very promising approach, as I will show today. And the key of a data simulation approach is such that it starts, of course, with a multivariable partial differential equation, but it can substantiate these free variables with data constraints, right? Eventually, you can reduce the system to an ODE, like ordinary differential equation. That's how we solve a PDE in general, right? And of course, this whole approach can be very flexible. For example, you can choose to substitute which variable and leave which variable as an unknown, right? So that's basically how you formulate your scientific problem, right? So in other words, with data simulation, you can really formulate and solve a lot of interesting problems. Here I will take the boundary condition as an example, and really the boundary condition is probably the largest uncertainty or the most important variable of Earth's evolution. For why we say that, so here I will give you some examples. Let's take this as a little class, exercise, right? In-class exercise, and I will basically formulate 4 different types of boundary conditions. For example, the domain of the model, right? The geometry of the model. Let's say for subduction, which is very important for plate tectonics, the location of the trench, relative to the model geometry or boundary, for example, and then the reality on the boundary, and also the far field effect for a model, right? I will go through them one by one. For example, model domain. So if we choose a model like this, right? Basically, it's a box that represents the subduction process that extends depths to the depths of 2,500 kilometers, really deep, almost the common boundary, right? Then you can imagine when you simulate subduction, you push the surface and generate subduction, the slab can easily reach the lower mantle, which is what we talk a lot about, right? This is a whole mantle convection concept. But if the model box, you choose it to be only, 1,000 kilometer deep maximum, right? Then, no matter what you do, you cannot get this geometry, right? So then the slab would look like this, right? So this is basically the same, everything else is the same except the depth of the box, and you get different answers, right? You get like penetrating slab versus stagnant slab. I mean, this is just a kind of like a pitfall of numerical modeling that people should keep in mind. Another example is the location of the trench. So say you still have a 2D original box that you mimic subduction. If you say put the trench on the left corner of it, right, then your slab can reach to the mantle, and you generate this kind of return flow, right? I mean, flow going with the slab. And you can easily imagine that the upper plate here is kind of moving toward the trench. You may argue, well, this is the way you can generate, extension or compression, etc., right? But you're highlighting this horizontal flow in this case. But what if you put the trench in the middle, right? In this case, the slab, of course, will naturally go to the right, and then you only have a little space for the return flow to happen. And in this case, the return flow would look like this, right? And then what is really catching your eye here is this very rapid upwelling, right? And people may say, well, this is a mantle plume. Well, is it true or not, right? I mean, I'm just saying that this can be influenced by the boundary condition that you choose somewhat arbitrarily. Okay, so the reality of the boundary is, so here I mean, you can do nothing about the reality. For the upper case, you just give it some surface velocity, or you don't even give it any velocity, right? Just like dripping or sinking down. So, but in this case, you can see that you get this symmetric subduction, which is not Earth-like, right? On the boundary here also, right? Of course, we don't want this. I mean, conceptually, this is fine, but for real Earth, this is not relevant. For the lower case, this is a data assimilation model, and people do impose velocity at the surface. And there's actually, they also use the yielding for the plate boundary. So this is a lot better than the upper one. You can see that the subduction at least is asymmetric like the real Earth. But very often you would have this sticky surface problem where the slab is stuck on the surface before it eventually entering the mantle, right? So we don't want this happen too often. What do we mean by far field effect? The last one is like so this is the paper we just get published, and you can see that this is upper one is a global model, but both these are actually 2 models and showing along this red line, the cross section in Western Pacific. The lower one is a very large scale regional model, 3D, like the green the green area. They are both whole mantle in depth. But you can see that their mantle structure predicted at the present day, as shown here, they are dramatically different, right? The upper one, you have the stagnant slab and the lower mantle slab that is far to the left. But on the right hand, everything is to the right, and you don't have stagnation. You have a steep subduction, right? The only difference in this case is the geometry of the model. So the one on the bottom is a regional. In other words, the walls on the sides are non-penetratable. But the one on the top, there's in and out flow, right? So it's more natural. So what this means that the far field effect, which is beyond this box here, is controlling this dynamics of E station. So it's very important. Okay, well, I've actually spent quite a lot of time on this one. So the to summarize this slide, you can say that the boundary condition really very strongly influences or even determines the results, right? And a lot of these can be artificial, you know. So and then on the other hand, this is a good thing because in theory, the Earth's post-evolution, because the boundary condition is so important, right? If we know the boundary condition, we actually can fairly well recover the evolution, right? And now we'll play a little movie here. This is a quite well-known.
Low Reynolds number flows are reversible when the direction of motion of the boundaries which gave rise to the flow is reversed. This may lead to some surprising situations, which might almost make one believe that the fluid has a memory of its own. Here are two concentric cylinders. The fluid can be moved by turning the inner cylinder with this handle. The annulus between them is filled with glycerine. Into this space, I introduce some dye, which stays put owing to the high viscosity of the glycerine. Note its position before I start turning it. I now turn it 4 times, pushing the handle clockwise. The dye seems to mix as a drop of milk mixes when it is stirred into a cup of tea.
So here, let me quickly pause. I mean, 4 turns, you know, of this little cylinder is almost like 4 Wilson cycles for Earth, right? Because this center cylinders are like the mantle shell. Okay, let's see what happened next.
Now I reverse the direction. And after turning exactly 4 turns, the dyed area reappears in its original position, with a little fuzziness due to molecular diffusion.
Okay, and that's what we call the kinematic reversibility. So for this sticky fluid, like the Earth's mantle, it's quite reversible. I mean, it's very different from the atmosphere or the ocean, right? It's really a very low Reynolds number fluid. So in other words, with known boundary condition, we actually can fairly reasonably reproduce the evolution of the interior of the Earth. So, I mean, you can do other things, of course, right? If you know the boundary condition and you know other constraints, you can diagnose or, you know, constrain the mantle properties such as viscosity or density, etc. You know, I will not have time to talk about all these, but, you know, if you design this experiment properly, you can also use this whole theory or process to further improve the plate reconstructions. You know, we know there's a lot of uncertainties of plate reconstructions and tectonic, you know, mechanisms, etc. Right? So these things can also be be treated using data simulation models. So then, what is data simulation? Right here, I call this geodynamic data simulation or GDA. So we are basically talking about 2 types of data simulation. The first one is a forward in time exercise. So the chart here shows the horizontal axis shows time from past to present, and the vertical axis shows basically the depths, in other words, the volume, right? The 3D interior, you can imagine. So during the past, we know relatively little about the Earth's interior, and with the geology, right? We really don't. We know the geology record, but we don't know what caused it, right? Because we don't know the interior state. But over time, we have a relatively good record of the surface motion. We call it, you know, plate motion or plate reconstruction, etc. But with time, right, if you say apply this data simulation technique, you know, you start with a relatively poorly known or even empty mantle, and you start to impose or assimilate this plate motion at the surface at the boundary condition. Then you start to generate convection, you know, upwelling, even plumes, right? And then toward the present day, if you happen to have the right parameter, when I say that, I mean, you do have some freedom to tune this model parameter like viscosity, right? And then there's a good chance you can get a mantle structure at the present day that resembles closely with seismic observation, right? Or geophysical observation, like tomography, anisotropy, even like magnetotelluric imaging, for example. This is one way, right? You start with a pretty known state, and by gradually inputting surface constraint into the system, you eventually get a well-constrained state at the final time. This is called forward. But then backward is just the opposite, right? You start with a very well-imaged present-day 3D structure, and then let things go backward, right? So basically, you reverse everything. You reverse the plane motion, and then you do the opposite of time integration. And of course, in reality, things doesn't work like this. We actually are talking about effective way, right? This is effectively how this method works. And this is a backward in time, or called adjoint data assimilation. And both of these are actually well-known methods. These are weather forecasting techniques very commonly used, especially in the past. And also combining these two, we can also generate some kind of a hybrid version of this data assimilation. I will not spend too much time on that. And now let's look at some examples of the forward data assimilation. Right? So what is data assimilation? It's actually a hard definition. I mean, I don't have a good definition, but basically any model that takes in observation as input, you can call data assimilation, right? So there are basically different degrees of assimilation. So these are 4 different types, roughly following the age while they were created. Like, Carolina and Mark Richard, they did this pioneering work, this is decades ago, and really groundbreaking at that time. So basically they prescribe the subducting slab using, spherical harmonic, basically like a little blobs of mass anomaly, right? And to pretend this is a sinking slab. It works quite well, for some example. And given the time, that's really advancing at that time. But with time, we want better and better models. So these are 3 relatively recent models. And you can see that these are all finite element or finite volume. Anyway, so these are numerical models, right? More Earth-like than the first one, of course, because they're much younger. But still, these models treat subduction differently. Subduction, I have to say that, is the most important or most difficult, most challenging part of data assimilation, because all kinds of singularity or discontinuity happen around this process. Let's look at the bottom one. So this one actually is really easy to understand. It's basically this model just takes the surface velocity at the boundary condition, and then push it with time. And also at the plate boundary, they also define the boundary to be weak, right? And then you generate slabs, right? And of course, you can see that the slab can be chunky, can be blobby at some point. I call it sticky surface problem, right? So in other words, the mass at the surface, the mass flux is not necessarily always the same throughout the subduction process. This is common for this relatively simple treatment of assimilation. So in the lower right, if you further, as I said, further prescribe like a yielding, and you can get slightly different behavior, but it's the same problem, the sticky surface problem, right? And the slab doesn't look like always like directly going to the mantle, but it's rather reluctant and to stock on the surface. The upper right, this slab looks much nicer. You can see that it's very natural looking. But the only caveat here is that this slab is parameterized. In other words, it's prescribed, right? So these are defined. So this structure is not it's not self-evolving. So it's not very flexible. So in our exercise, we actually spent almost 10 years dealing with these difficulties, and we eventually come up with a thermochemical formulation. So we use all information we could have, the location of the trench, the rheology, the plasticity, and the compositional and the temperature effect. This is the composition, this is temperature, this is viscosity and temperature. And eventually, when we look at the 2 classes of models, like the one on the left is the nicer looking model. In the previous ones, they're pure thermal. So the upper mantle slabs are pretty linear. But as I said, these are non-deformable slabs because it's prescribed, right? And they all look the same throughout time, the upper mantle, I mean. But in our case, the slabs, they are self-emerging. In other words, the slab can do whatever they want. So they can have changing dip angle, and they can even have, a break or, deformation like this. So it's really flexible and deformable. And to give you some more examples, this is the same set of models, but we're looking at the Pacific Northwest. This is the one the focus slab subducting below, say, Oregon. About 15 million years ago, very, very shallow depth, like 15 kilometer depth, 50, and above 100 kilometer. In the slab hinge, we have clearly we develop a regional gap, and you have this very crazy mantle flow coming up that we tied to the Columbia River flood basalt, right? And so this is an example showing that the slab is really flexible, it's deformable. And similarly, our model for South American subduction, the Nazca plate with the oceanic plateau subduction, you can see that they have very complicated but also natural looking or realistic looking geometry, because these white lines are beneath zone, these are observation. So basically the slab geometry matches the observation quite well, right? But at the same time, we also see that the flat slab are actually all broken in the interior. This is actually a new feature, quite interesting. So this kind of results can only be generated when you allow the upper mantle slab to freely deform. Otherwise, you cannot, right? Another example is even more recent paper. This is subduction below Western Pacific, basically East Asia. And we can see that this is the late Cretaceous. We have a very large scale flat slab. Right? When the flat subduction happened, it basically thinned the mantle lithosphere. The LAB is reduced a lot, and eventually the surface topography reduces. And this is a characteristic geomorphology feature of East Asia. Okay, so now I will give you another quick example about this backward. I need to speed up. Backward data assimilation. So as I said, we start with the present day mantle structure. So this is the far long slab, we usually call it. At the surface, this is the topography. Blue is substance, red is uplift. So if we go backward in time, you can see that this subduction is undone, right? So basically, you see the past subduction, especially in the late Cretaceous, we have a very large scale flat subduction where the surface was pulled down that formed the interior seaway, right? So GRD in this case is very important, right? So with GRD, we can further constrain the mantle viscosity, for example. This is the backward, and then I will give you also another example, so-called hybrid. So it's basically a mixture of the forward and the backward. This is based on the Earthscope, US array tomography, the Schmann and Lin 2014. The upper panel shows the tomography at different depths and also cross section through the hotspot track into the Craton interior. And the bottom one shows the model results correspondingly. And you can see that they are really quite nicely correlated. But I want to point out that this little piece of slab, the one of Fuka, actually is different from the tomography. In the tomography, the slab is a vertical close to the surface. We know that's a vertical smearing of body wave tomography. But in our model, it's more natural looking. This is resolved from the forward data simulation approach. Right? Other features, they are from the tomography directly based on the adjoint approach. Okay, so now let me move on to, I need to move up. Okay, well, as long as we cover that part, we will be fast. I will give you a quick summary about what we did for the Western US subduction, right? This is a simple model setup. The initial condition here, the velocity, the temperature field at about 35 kilometers, these are all based on the reconstruction. So we call them data, right? Actually, it's kind of a metadata. So in the cross section, we see that the slab will naturally emerge, right? So they will evolve. And with time, the slab will grow and actually even break. And at present day, they will form very complex structure. And this complicated structure actually is not arbitrary. It's actually is constrained by tomography. So these three green lines, these are based on 4 different tomography models, right? They all have like several segments. And in the map view, the evolution look like this. Over time, initially continuous slab will break into pieces, and eventually that's what you see at the present day. So highly segmented one focus slab below Western US. An interesting feature we found here is that the breaking process actually happened about 15 million years. You see the slab tear here. I already showed the 3D image. And of course, the comparison with tomography on the top and the model results at the bottom, they're quite remarkable, right? So this gives us confidence that the past evolution must be reasonable too. So this is like in the mid-miles in time, we see the breaking of the slab tear, of the slab hinge, and that we correlate to the Columbia River flood basalt. So spatially and temporally, the features all correlate, right? So in this case, we propose that a large igneous province on Earth does not necessarily require a plume, because this case we don't have a plume. But is a plume really needed, right? This is still kind of an open question at that time. Then we did more tests. We literally add in a plume below the slab tear, and we found that, well, for most of the time, the plume will be covered by the sinking slab. And if the plume happens to get through, it has to be at the right time and the right location, right? In other words, it's a low probability scenario. But of course, this is still a forward model, right? Let's see what an inverse model would do. So this is, again, the same cross-section I showed at the present day, but now with flow vectors because it's a geodynamic model now. If we go backward in time using the hybrid approach, what do you see that the plume here is actually kind of staying kind of stationary, but it's really not connecting with the surface at any time, very prominently. But instead, what is seen today, that is kind of like a right below the hotspot track, Yellowstone and Newberry, these hot anomalies, they actually move mostly horizontally. Eventually, they move to the ocean. In other words, the heat below the Yellowstone hotspot system, we found, at least according to this model, they are predominantly from the shallow Pacific mantle, not the Yellowstone plume. So this is another view looking at the two systems of hot anomaly. This is the shallow one. This is the deep one. They move relatively separately. So to summarize that, we kind of argue that this the shallow anomaly intruding to the Western U.S. is the main heat source for the intraplate volcanic system of Western U.S. The plume is kind of doing something, but it's not a major contribution. And this whole system is controlled by the sinking slabs below the East Coast, the former Farallon slab, with the newer slab on the West Coast. There's a competition, right? That's why there's a branching flow forming two opposite hotspot tracks. Well, this is just a model, but then we need more validation, right? This is actually looking at anisotropy using the same model. The horizontal flow, as I highlight, is really important for the eastward progression of hotspot tracks. And based on this flow, we predict the anisotropy. The black one is the observation, and the green one is the prediction. And they see that they largely match, like the circular pattern, especially, quite remarkably. And so here we look at the physics, right? These are basically the horizontal flow dominant phenomenon. And of course, based on the same thing, you can also look at the topography variation. These are just the same sequence. You can see that the high topography really follow the migration of the hot anomaly. And if you look at the region of Colorado Plateau, is relatively stable. And if we compare with some observational constraint, and the model prediction on the top three curves for three locations, they match the observation for these regions. And then, as I said, this is the heavy duty part. Most recently, we also look at the continental scale flow pattern. We look at two depths. The red arrows shows like 150 kilometer depths, and the green ones are at 500 kilometer. This is a highly 3D flow below the Western U.S. And of course, that's because at the same time, the lithosphere thickness variation also is dramatic. So with these, together, we can reproduce the stress, the crustal stress state fairly well. I mean, not perfect, of course. There are some deviations, but overall, it's not bad. And based on two data sets, we can reproduce the overall stress state. And these are all independent validation, right? As I said, data simulation models, there's no standard definition. And the more data, usually the better, right? Or the more credible you can imagine. Okay, so for the rest of the time, I will get into a little more discussion about other topics, like subduction dynamics in general. So this is looking at a forward subduction model of Western Pacific. So you're looking at Izanagi subduction at 120 early Cretaceous into the end of the Izanagi subduction by 60 MA. And then by present day, you see Pacific subduction, right? So basically here you see a variety of slab geometry, like from like a normal subduction to flat subduction to stagnant slabs. And that's the tomography is basically confirming the present day geometry. On the Eastern Pacific, which is dominated by the Farallon subduction, of course, at the same time, you see similar behavior, steep subduction, flat subduction, and stagnant slab, right? So it's remarkably similar. And the Pacific, two sides of the Pacific are almost like a mirror image of each other. So based on this, we kind of propose that the life cycle of a single oceanic plate subduction looks like this. In the first stage, in the early stage, you have relatively steep subduction and upper plate extension, and in the later stage, you start to have flat slab and upper plate compression, and eventually the flat slab will terminate. But the termination of the flat slab is actually an open question. What we found here is that the flat slab will continually move inland, but eventually it will just founder. It will peel off from the upper plate, and that generates a huge tear in the slab, and that causes the mantle flow to go through from the ocean side to the inland side. At the same time, because it's the end of the oceanic plate, the seafloor, and so the mid-ocean ridge is also approaching the trench. I will look at this a little closely. So this is the same model you just saw. So for the Cretaceous flat slab, what we found is that it's really the pressure below the overriding plate. The pressure is getting lower and lower. The blue color here is the low pressure. It's like a formation of a hurricane or a tornado, right? The center is low pressure that basically sucks material towards it, and the oceanic plate becomes part of the wall, right? It becomes flattened. And that is what we said. It has very direct geological implication. The stagnant slab is also another matter of debate. What we found here is that the stagnant slab here is predominantly driven by the low pressure in the East Asia, like here, that generated very strong landward flow, and that flow actually diverted the slab to the inland part that formed the stagnant slab. And the rightmost panel shows the mismatch between the predicted and observed SKS splitting, and the color of the Eastern Asia is pretty blue, right? So in other words, the prediction is fairly good. Oops, sorry. A little technical thing here. Okay, good. So now, another aspect is this flat slab to stagnant slab transition seems to be pretty universal, at least for the two sides of the Pacific Ocean. So during the flat to stagnant transition, we also observed something very interesting. That is for the Izanagi slab subduction, which is flat during the late Cretaceous, and then it basically broke. And part of the reason is because the mid-ocean ridge is coming, the slab becomes too weak to sustain a continuous, strong guide. And when that breaks, there's a very strong landward flow that basically, we call that a mantle wind, right? So that means mantle wind has two roles. First, the mantle wind eventually caused the Pacific plate to subduct. And on the other hand, the mantle wind during a lot of time, because there's no slab above, so this mantle wind directly applied to the base of the overriding plate, and that caused the overriding plate to extend. That is formation of the marginal basins. So this is the same model. What you're seeing here is that landward flow caused the formation of the East China Sea. So the background color here shows the model predicted stress state. So blue here means extension, red means compression, and the black bars are the compressional maximum stress. So overall, the blue region, as you can see, that it very nicely reproduces the observed, the magenta contour. This is the observed basin extension history. Okay, so it's a nice validation to the model as well. Okay, another interesting thing is this phenomenon is actually happening globally. So we call this trench parallel mid-ocean ridge subduction, and that caused the back arc extension. Because the mid-ocean ridge subduction marks the end of a oceanic plate, right? Okay, so finally, I will use a few minutes talking about the Craton evolution. This sounds like a different topic, but actually it's really a derivative of this kind of study. So the starting point here is still subduction, right? So like, for example, here we are modeling the Nazca subduction, and the result of that is mantle flow, like these vectors. So based on the flow, naturally we can calculate anisotropy. So these are our surface level tomography derived anisotropy at 150, 200, all the way to the base of the asthenosphere. And you can see that the observation, which is black, and the prediction, which is red, they match fairly well in the ocean region, right? And these big arrows are the mantle flow, the converging flow. So this gives us confidence that we probably get the mantle flow right. But what is not matching very well is the continental region. You can see that there's a large, errors. And usually people would just give up saying, well, the content is too complicated, right? That's how people usually think about it. But the fact that we can model the ocean fairly well give us a chance to further look into the content. That's an opportunity, right? So what we did is we look closely at the content, and we compare the Cenozoic mantle flow induced fabric with the observed anisotropy fabric. We found that something very interesting. That is about 100 kilometers is a divide, right? Above 100 kilometers, the observation and the mantle flow has no correlation. But below that, we start to have very strong correlation, which is the blue color, in regions where we have high topography and rough topography Craton. So these are the well, we basically argue that 100 kilometers is a depth where the upper lithosphere and lower lithosphere decouples. Because the good correlation at the deeper depths means that the Craton at this depth is reset, right? It's deformed at least. And of course, then based on other evidence, I will not have time to talk about, like surface topography, gravity, geology, mantle structure. We propose that these high topography region where we also have the anisotropy reset at the bottom is a sign of past delamination. So to show you this present day state, so below the Atlantic Ocean, in the upper mantle, we see these very prominent pieces of fast anomaly. And so this same story, we basically extended that further. These are no longer data assimilation models, but it's derived from that. Then we have 3 papers in a row where we show that the mantle lithosphere below the Craton is really high density instead of like neutrally dense or even positive density. And this paper just came out. What we argue and show that is that during the plume lithosphere interaction, the lower lithosphere could really delaminate and cause global changes in many things. For example, in topography, right? This is the Craton conformity. It corresponds to the separation of rodinia and cause surface uplifts and erosion. And then afterwards, the delaminated material actually relaminates to the base of the lithosphere, and that caused the lithosphere to restore, to cool, and then to densify, eventually cause the surface to sink. These are intracratonic basins. And the same thing happened during the separation of Pangaea toward the present day. And we even have a little movie to show that this is dynamically feasible. When you have delamination, the material, after a while, initially it's cold and dense. Then when the delaminates, it warms up, eventually it comes back to the surface. And when it cools down to a certain state, it starts to delaminate again, right? So it's an episodic process. And as a consequence, the lower lithosphere delamination also make the lower lithosphere anisotropy, the radial anisotropy, to be opposite to the upper lithosphere. This is 70 kilometers, this is the 150, right? So in the 150 kilometer, VSV is larger than VSH globally, meaning that this is the vertical deformation dominant. And based on that, we further propose this is what we think happened during the past 2 continental supercontinental cycles. Okay, I'm pretty much done with the content, but I will summarize this with a little bit of a future thought. I think the GDA development can allow us to do more things. For example, like a multi-scale dynamic coupling. This is an example of what we are working on right now. So again, the Western US mantle flow, it can, it's a large-scale mantle flow, and it generates large-scale stress at the base of the lithosphere. But that stress can be partitioned if you have a fine-scale lithosphere structure, say with a lot of fine scales defined by rheology, for example, then you can reproduce. This is reproduced the GPS motion, right? The black is the observation, red is prediction, I think, and we did a fairly good job, right? And then furthermore, you can even generate the very localized, the strain rate, like the red, so background color, the yellow is high strain rate correspond to the localized earthquake belt. And both the stress state and the focal magnitude earthquakes are corresponding to each other. And this is the one thing, right? Multi-scale physics and also cross-disciplinary modeling. And what I'm talking about here is, this is an example of dynamic topography, mantle flow-driven topography causing the surface topography to change. And that caused the rivers and the marine inundation and also the sediment migration, the basin strata evolution, etc. All these surface processes to evolve, coherently with the mantle driving force. Finally, I still have one more slide. Then stop there. I think this can be even pushed even further. I mean, we haven't done much work here, but it's just a thought, right? So Earth's interior can drive even maybe climate or environmental change eventually. I have a nice figure here showing that this is actually our model. We can now reproduce the subducting slabs and the rising plumes, and they are all, match observation fairly well. And at the surface, you can, apply the landscape evolution model I just showed in the previous slide. We have rivers on land, and you can further couple that with the real liquid, the fluid layer, like the ocean and the atmosphere, right? These are ocean current. Oh, I have the labels here, and the temperature at the surface. Wow, that's of course a long goal. Okay, now let me conclude here. I will say that the geodynamic model with data assimilation, it's quite special because it allocates data into this coherent 4D frame. It's actually no longer a model. I mean, I would call this it's changing this data poor model into a data rich model. It's really an observational. We're playing with data basically, right? I call this observational geodynamics, or some other people call it applied geodynamics, right? Anyway, it's different because we're playing with a lot of observation. And so again, reproducing the subduction history of oceanic plate, that's always our starting point, allow us to quantify, the dynamic process of the Earth and also the surface tectonics driving mechanism. Another important thing is like understanding the ocean allows us to further understand the continent, especially the Cratons. And this is still a relatively new direction, and that has many exciting implications. In the end, I would say that the GPA also provides a way forward for more realistic, more complex Earth models. And of course, people have different opinions on this one, but I would say that at least there's a hope, right? So it represents a promising way to solving more complex Earth systems. For example, like multi-scale, multidisciplinary, or integrated Earth system problems. So with that, I will stop here and take some questions. Thank you very much.
Excellent. Thank you very much, Dr. Liu. We have had a couple questions already come in, but I want to remind our audience that you're welcome to submit questions for today's presenter, and you can type those in using the Q&A box. And why don't I start with some of the questions that have already come in. This first one is from Michael, and it says, basin development in areas of thick lithosphere or high elevations should record the process of delamination. What basins do you think should be studied?
Okay, yeah, it's an interesting observation. So let me try to understand your question first. I think basin development to the first order, in the beginning, it should be a low topography, otherwise you cannot even have basins for the most case. But then if this if this thick lithosphere and high topography now, maybe it's because it actually rebounds and the topography they overall change over time. And that's of course one scenario. I mean, it could also still be, it's always high topography, but it's a local minimum, right? Then it's basically internally draining system that could also form basins. Okay. Whether this record delamination, it could. I cannot say for sure, but what I showed here is intracratonic basin. There are still, most of them are still low, like the North American, like the Illinois Basin, Michigan Basin, they are still low. But you are right, like the Colorado Plateau is a high plateau. It has sediments in it. Like a Western Pacific, like East China, like this Ordis Plateau has a basin in it, right? And they must used to be low topography, but now they just pump up because of likely delamination. I like that word. I think so. Thank you.
All right, we've got a question here, a comment and a question here from Simon. So this is, correlation versus causations. Lijun, thank you for a great presentation. You show truly amazing matches to present-day observables, and no doubt your derived geohistory is a valid solution. But how do I know you have found the unique solution?
Oh, Simon, my friend, I mean, you always ask good questions. Yeah, I throw that slide in the beginning just for motivation. Yeah, we are always looking for the unique solution. I can never say I have the unique solution, to be honest. I would only say the solution will become more and more realistic only when you have more data or you have more validation. At this point, nothing is really unique. You're right. Yeah. So maybe I mean as I said, the definition of data assimilation is so not well defined yet. So I would hope in future that we can have much more data that we can assimilate into the same model, a coherent physical framework. And then at this stage, maybe we can more confidently say that this model is more unique. But still, I mean, I cannot say it's truly unique.
Maybe I'll build off of what you just mentioned about having more data to feed your models. And you talked about that various types of data are assimilated to drive the geodynamical models that you've shared with us. Would you mind just commenting briefly on kind of what some of the key pieces of data going in are? I mean, I assume seismic results, but if there are others that make a big difference or that maybe are harder to get, that are you're really keen to be able to get more of.
Right. Yeah. I probably didn't make that clear. That's right. And so basically, at this point, we need data that can cover the two ends of the equation. In this case, when you structural image, 3D image at the present day, that could be any geophysical image, right? Could be seismic, could be MT, could be attenuation. Well, attenuation is on the seismic image. So as long as it covers the 3D volume, that's a structured image we could have. But that's only for the present day, the snapshot of the evolutionary system. And then in the time domain, we also need data. And so far, we mostly use play reconstruction, which is play motion over time. But that, going further back in time, is a U-pose problem because we are running out of constraint. Another piece of a line of evidence along that dimension is geology. This is a very loosely defined field. I mean, geology is so big, right? So the data we use there, I would say mostly is the vertical motion data. These are the paleoaltimetry, basin substance, and paleoaltimetry. There could be more, well, Simon, you have more data. Maybe I can use your helium data at some point. I just don't want to give the limit. I think the more the better, but
yeah,
careful, Yeah.
Yeah. So we have had a few additional questions come in. This one is from Saria. It says, why is the VSV wave velocity generally larger than VSH wave velocity in the Earth's crust, particularly up to a depth of around 70 kilometers? What geological and structural factors contribute to this difference in size with wave velocities within Earth's crust?
Okay. I assume this is referring to this figure I showed. Let's see whether we say this correctly. What this figure shows here is the VSV is larger than VSH below 70 kilometers. I mean, greater than 70 kilometers at 150. So this, to my interpretation, of course, based on the context I gave, delamination, for example, I would argue this is reflecting a more vertical deforming history, so which is delamination and relamination. While the upper lithosphere 70 kilometers, for example, is VSH dominant. So this is horizontal fabric dominant. So where the deformation we can say is mostly shearing in the lateral plane. That is not delamination at least. So we are saying the upper and lower lithosphere, they are decoupled.
Okay.
So I hope that answers your question.
Thank you for clarifying that. We have a question from Jiao Tao here that says, in the implications on Craton evolution, what is the role of purely thermal evolution, so like cooling subsidence, in addition to delamination and relamination?
Oh, Jiao Tao, yeah, very nice question. What's the role of pure thermal evolution? Yeah, so I would say that let me go to, I do have a yeah, maybe here. Yeah, like the basins here. So we're looking at the global Craton basins. They have remarkable temporal coincidence, although spatially very distant. So according to our understanding, we try to explain this basin substance using the restoration, the gradual restoration and cooling and densification of the lithosphere over time. That's after the delaminated material relaminates. And then it freezes in and starts to cool and to cool down the surface. So in this case, you are right. It's actually mostly a cooling process. So we actually are not considering the compositional effect, but in reality, it could. There are actually studies showing that the mesosomatism or refertilization, etc., of the lower lithosphere could cause further subsidence. So at least for our models, we are mostly concerned with cooling. It's a long-term process.